Good morning, my name is Jason Blackford. I'm from the Air Force Institute of Technology, and I'm here to talk about today my paper on online skill level classification of real-time strategy game players. Just a quick overview. We'll get into a background, what we based our research, our investigation on, where our investigation took us, the results, and future work. Just to put it out front, the games that we used for our investigation include StarCraft Brood Wars and the Balanced Annihilation game for the Spring Engine. Setting up our work, what led us down the road that we decided to take was the work here by Weber and Mattis, 2009. They were able to successfully demonstrate online strategy classification for the StarCraft Brood War game. Essentially, they defined a set of StarCraft strategy schemas for each of the StarCraft races, including Terran, Zerg, and Protoss. From expert player log data, they collected expert player log data, and from that, they derived player feature vectors that timestamped strategic decision points while the player played the game. Then they took those feature vectors and applied supervised learning algorithms to classify the player features by strategy. So their representation, the main thing that we took from this work was how they were able to use strategic decision points to classify player strategy based on a set of strategy schemas that they defined. So kind of taking this directly from Weber and Mattis in 2009, the goal of their representation, so the goal of our representation is to capture the timing aspects of a player's strategic decisions in a game, enabling the prediction of distinct strategies and the timing of the opponent's actions. So that's the key takeaway from this chart and from that paper where our investigation took us, was strategic decisions, being able to use strategic decisions from a player's log data to classify the player, or maybe from another perspective in player modeling, not just strategy classification, but can we use it for skill level? Is there a way to take these strategic decisions and maybe analyze them and come up with a way to score or measure skill level? The next work that really inspired our investigation was the work done by Aventur 2012. Aventur states plainly that experts tend to have better motor skills and better visual spatial attention and make faster decisions than novices. I think this is a fair assumption and a very rational thought. Aventur was able to demonstrate successfully a limited online capability for strategy classification. So Aventur utilized 44 features, including actions per minute, to model player skill level in the StarCraft 2 game with some great success. And the key point here, though, is that this approach that Aventur used included APM. So APM is not strategic decisions, it's actions per minute. So how many mouse clicks did a player take? So that's a pretty common metric I think most people are familiar with. This technique that Aventur used requires the use of support vector machine to work. So we appreciated the approach used by Aventur. Obviously, it had some limited success, but it's a more complex approach, and we wanted to come up with something a little simpler, just maybe a simple metric, something that could be calculated very quickly while the game is played by an RTA, by someone playing the game. So this led us to our investigation. So given a known strategy schema and a player's execution of the strategy, so their strategic decisions, can player skill level be measured in real time? So our intention is to use the metric for real-time play, or in an online fashion to classify the player. The reason we wanted to come up with the metric to begin with was our primary research was in online build order optimization. So we actually had success in building in solving the build order problem in a unique way. And so what we wanted to do was try to see if we could come up with an evaluation scheme to evaluate how one player does executing a strategy versus another player. So was there a quick way to do that, a simple metric? And kind of what inspired this is wargaming. Coming from the Air Force Institute Technology, something we're interested in is wargaming. RTS games fit that domain fairly well, and so that's kind of where our perspective was, where we were trying to go with this. Investigation and strategic decisions. So the strategic decisions is the critical piece here, and I want to make sure it's clearly understood what the strategic decisions are. So strategic decisions are reflected in player log data. So if you've ever played the StarCraft game or have looked at player logs, player log contains every action a player takes. Each action has a name and an associated timestamp in the log data. From there, what we do is we build a feature vector which is just strategic decisions only. So the way we identify these strategic decisions relate directly to the player's technology tree for the associated race or game that they're playing. So technology tree captures unit type creations, upgrades, technology advancements, things of that nature. And so strategic decisions are determined by a specific RTS game strategy and its goals. So each RTS game strategy is going to have a different set of strategic decisions that are going to be made. There's going to be some overlap, but they'll be different. And you're also going to have a different set of goals that you're trying to accomplish for a specific strategy. So again, not the same as actions per minute. Again, strategic decisions were used successfully by Weber and Mattis to determine strategy of expert players for StarCraft Brood War. So in measuring the strategy execution, the first thing, and this kind of shaped our build order technique, was what is strategy execution? And so we said it consists of two components. First is good goal ordering. So if you want to have skilled strategy execution, you have to have good goal ordering, which is defining a plan of execution that takes into consideration resource allocations, dependencies between goals, and the total time to execute a known strategy. The next component is good build order execution. So this affects the time at which a goal is reached, and therefore the overall execution speed of a strategy. And now this leads us to the the distance between strategic decisions metric that we came up with. Essentially, we broke it. There's two types of the DBD metric. There's the arithmetic DBD and the geometric DBD. When you look at them, they're essentially averages with an incorporated penalty. So arithmetic DBD provides a single value or score that shows which player executed the strategy more quickly throughout a single game session when compared to another player's DBD score. So keep in mind that DBD is relative to other DBDs. So if you're going to assess a player and you measure a DBD score, it doesn't tell you a lot of information unless you know what other DBD scores. So if you have a set of experts and you know their DBD score, now you have some information that you can work with to determine, well, I have an unknown player, I've measured their DBD score, so based off how the experts do, where does this player fall at? Are they doing well or are they not doing well? So there's some thresholding that needs to be worked out. Geometric DBD is used, it shows more of the consistency between strategic decisions. So these equations here, which you can see at the top, DI plus 1 and DI, those are the strategic decision timestamps when a decision was made. Epsilon is a penalty of so many game cycles. We discussed this more in the paper. And N is strategic decisions defined in a strategy schema that were not made. So if the player didn't make a strategic decision, then we count that as one strategic decision that wasn't made. E is the total number of strategic decisions that can be made for a specific strategy. So the main points are arithmetic DBD allows you to captures which player executed the strategy the fastest overall, and geometric DBD shows timing consistencies, which player had a tighter timing consistency between their strategy execution. So the first data set we looked at was StarCraft. We took the data set that Weber and Mattis used for their 2009 paper on strategy classification, some of the data, and the set that we chose was the Terran versus the Zerg race. The Terran have 3 strategies listed in this table, including bio, dropship, and 2-factory. And for each strategy, we had an associated number of expert feature vectors, 740, 66, and 18. For novice, we went ahead and played the game ourselves. We were new to the StarCraft game, and we're by no means ranked players, and so we came up with 5. Looking at the bottom of the chart here, you see a sample player feature vector. What I wanted to show you was really what do we mean by strategic decisions, just kind of give you a small example. This is a very contrived example of it. I just wanted to kind of show what the features look like. So for the StarCraft game, this is the bio strategy, for example. This is usually a strategy schema will consist of 55 strategic decisions. Here we have just a small number. So depot, when was the first depot made? When was the first gas refinery created? How about the second one? When was the first command center? So expansion is more about command center. When was the 4th command center built? When was the first barracks built? So you don't see actions per minute here. You're seeing strategic decisions. All of these can be tied back. These decisions here can be tied back to the technology tree of the player. So applying the arithmetic DBD on our data set, we wanted to see how we could separate or if we could determine scores for novice players and expert players. So we used the bio strategy for the 5 novice players that we had, feature vectors that we had, and the 740 expert players. On the left, you see the scores, the arithmetic scores, when there's no penalty. So when epsilon is 0, you see the overlap. When epsilon is not 0, we actually had it in this case 1,000, and we talk more of that in the paper, you see a separation, which you would expect to see. And the reason why a penalty is important for arithmetic DBD is because if you don't penalize an indecisive player for not making decisions, if they only make 2 decisions, they could potentially seem very good at what they're doing. So you want to penalize for non-decisions. And that's what you're seeing here. And in a way, this validates the use of a penalty to get that separation of the data between experts and novice. More interesting, we went ahead and calculated geometric DBD and arithmetic DBD for the averages for each strategy that we looked at. So the results in the tables that you can see below suggest that there's a distinctive DBD range that experts operate within across the 3 strategies. So it's interesting because what this could mean potentially is that it doesn't matter which strategy an expert's executing, they're going to achieve the relatively close to the same DBD score no matter the strategy they're executing. So that's very interesting and useful. And you can see that in our chart between the means and the standard deviations of the scores. They're all very close to each other. Again, this was for all expert data, no novice data. So the next game that we looked at was Balanced Annihilation. And so Balanced Annihilation, we did our primary research in that, and we had 2 agents that we were working with, 2 artificial agents that in long-term goal was to use them as opponents against a player. Agent Boo is the name of one player, and Agent LJD. And I'll get into more of that in a little bit. But we had 3 strategies we looked at: Tank Rush, Expansion, and Turtle. We had 5 feature vectors from each. Here is another sample player feature vector for the Balanced Annihilation game. And again, just there to illustrate a little more. This chart shows how the 2 agents did against each other. So you see Agent Boo here at the top with the gray arrow, and Agent LJD who's captured with the white arrow. What we're capturing here is their build order execution and who's able to execute each goal faster. So each column in this chart represents a goal, and these arrows include the build orders used to achieve that goal. So what you see is Agent Boo, through all 4 goals, is able to obtain each goal faster by seconds, 20 seconds, 10 seconds here and there. And so hence the star next to Agent Boo's name. So what we wanted to know is, is our DBD metric able to also observe from feature vectors or strategic decision making of the agents, that Agent Boo should score better in DBD. Now keep in mind that LJD and Boo both have the same goal ordering. The difference is that LJD is a scripted agent, and Agent Boo uses a multi-objective evolutionary algorithm for creating the build orders and executing those. So that's the only difference. So we would expect to see close scores that are close together. So these are the results for the tank rush strategy represented by TR. That's the first two columns at the top. You see that Agent Boo does get the lower DBD scores, which validates the DBD metric is working the way it is able to show us what we expected it to show us. For the other strategies, you'll see slight variations. Those we talked to that in the paper. Not all the goals for those are captured in this table, but in general, you would still expect to see close DBD scores between the two characters. And just to see, no, okay, so it's interesting where you can see how the scores play together. So results, applying DBD, so what we've concluded, kind of the main things that came out of this, applying DBD to the StarCraft Brood War game reveals that expert players score within a specific DBD range regardless of the strategy being executed. That's what our work suggests currently that we've done. The DBD metric is able to identify a more skilled player when the same strategy is executed by two players, as demonstrated in our balanced annihilation experimentation. So the results that we showed for that, you could see for Tank Rush, Agent Boo clearly executed faster than Agent LJD, and the DBD metric confirmed that observation. Other observations are presented in our paper. For future work, it's important that we explore the use of a larger data set containing expert, intermediate, and beginner players and determine some thresholds. So given a game and a set of strategies, what are the thresholds, the DBD thresholds for experts, intermediates, and beginners? And then also demonstrate the use of DBD to build a player model used by an AI opponent to adjust how it engages the player. So given that DBD is a simple computation, we still need to demonstrate its potential as an online capability by incorporating it into a player model, or excuse me, into the game early on, so that it can build a player model to be used by an AI. So that concludes the presentation. Thank you for listening.